Okay, let's take a look at some ideas coming out of Chapter 8. This is the hypothesis testing. I can't even write. Let's fix that. Hypothesis testing. So the idea is that we start with an assumption, right? So we start with this assumption that if we had a particular population, and let's take a sample or a subgroup of this population that equally represents the whole group. So in other words, we have a sample that's a random sample, and if we apply a treatment to this sample, so we manipulate it in some way, we start with the assumption that the treatment has no effect. Okay, so we start with an assumption the treatment has no effect. Okay, what we want to do is find enough evidence that says that that is not likely. So in other words, we want to find enough evidence that we can reject that first assumption, and that evidence we would come up with would be the observation of an extremely unlikely event. Okay, so we want to find enough evidence to suggest otherwise. Our assumption is incorrect. Okay, and like I said, that enough evidence idea is to find, when you actually have a sample, you've applied the treatment to this sample, you get a value, usually the sample mean, let's say, or sometimes some other statistic, but you find a value and you say, okay, what's the likelihood of observing this value or something more extreme? And if the likelihood of observing that value is very small, and in other words, it's a very unlikely event, then that is enough evidence. Well, we set a standard, but typically we say, okay, this is enough evidence to say that our first initial assumption is not correct. Okay, so just to kind of, I don't know, give some background on this, the idea in mathematics is to do a proof by contradiction, to say, okay, well, let's assume this thing is true and then show that it's not true, and that's proof that something else is true. Okay, and that's when you have the assumption that it's either yes or no. Okay, you either are inside or you're outside. So if I can establish that you are not outside, that means you are definitely inside. Okay, that's the basic premise. But with statistics, we don't necessarily have a yes/no, such a clean, clearly defined boundary for a treatment working or not working, and measuring the effect or things like that. And so I want to go through an example in a moment and kind of talk about those ideas and give you a good sense of what the statistics is telling us. But before then, I want to kind of outline the hypothesis test start to finish and give you a sense of some of the mechanics of it. Okay, so there's two ways to go about doing a hypothesis test. So there's two ways, that's a S, to test. The first way would be to compare critical values with test values. So let me just write it and then I'll explain it. Compare critical values with test values. The critical values are going to be based on a set significance level. So these right here are going to be based on set significance level. So in other words, we set how unlikely we're going to allow something to be before we say that that is really unlikely. Okay, so this is the significance level is the alpha, and it's maybe it's 5%, let's say, as an example. Switch colors so you know it's an example. If it's 0.05, we're saying that if we could show that the probability of observing this test, the test value, the sample mean, is less than 5%, then that is what we're going to call unlikely. All right, in other words, it's significant. What we could do then is translate that alpha level 0.05 into a z-score and say, in other words, what z-score corresponds to that tail area of 5%, and then what we would do is compare our x bar that we get that's our test value, we would compare it with the so we would compute a z-score for our test value and compare that with the z-score of the critical value. And if we find that our z-score, so maybe I'll write it like this, if we find that our z-score from the test is less than or equal to the critical z, then we do nothing. But if we could show that our z-score from the test was more extreme than the critical value, then what we would say is we would reject the initial assumption. I'm going to change up the language in just a moment after I highlight some ideas. Okay, that's the idea. So what I'm suggesting, maybe this isn't so practical in terms of computation, maybe it's a little bit too finagling, but I just want to highlight this because this is a viable way for a lot of fields to do comparisons if you rely on a significance level. I'm going to kind of pitch this idea that maybe we don't worry so much about the significance level and just compute the probability of observing this test score, in which case then we would do the second method. Okay, so if we had a observation from a sample, the second way we could test it is we would compare, so the second way is that we would compare what we call the p-value and the alpha, the level of significance, or the significance level. Significance level. So in other words, if, and I'll write this in a different color, if our p-value that we calculate is less than the alpha that we've set, in other words, if we can show that the probability of observing our test score, the p-value is the probability of observing our test score or something more extreme, if we can show that that probability is less than the significance level, then that is enough information for us to go ahead and say that we can reject our initial assumption. Alright, what we're trying to say is that the probability of observing our test score is less than the minimum probability for something being quote-unquote unlikely. Alright, so let me back up a little bit. I've already mentioned the significance level, but the p-value is just the probability of observing our test score or something more extreme. Okay, let me back up even further. When we have a hypothesis test, we always start with an initial assumption, and to give this a kind of a consistent reading, I'm going to call this the null hypothesis, null referencing 0 or the ground level. So the null hypothesis, I'm going to write the words and then show the symbols. The null hypothesis is expressed as this h sub 0. It's a subscript of 0. And the null hypothesis is, in a nutshell, saying that we assume that the treatment had no effect. Okay, so this is our assumption that the treatment had no effect. Okay, so typically we write this as the mean is equal to whatever the mean should be. Okay, and I'll kind of highlight that with an example. Okay, we could have a different hypothesis if we weren't looking at means. Maybe we were looking at proportions, in which case this part of the hypothesis would change. But it's still the basic statement that whatever we've manipulated, that manipulation had no effect on our statistics. In other words, the treatment for the drug, if the treatment is a drug, that drug did not influence anything in our population. Okay. We always compare this. I realize I didn't finish the word hypothesis. Okay, we always have to have a pre-planned alternative hypothesis. So in other words, before we go and collect data, we have to have a sense of what we want to see, or what we observe the data suggesting we should see. Okay, for every hypothesis test, in order to be objective, you must collect new data, or reprocess the data from a new standpoint. And so the alternative hypothesis is our pre-planned expectation. So we write this with an H with a subscript of 1. Some books use the subscript of A to reference alternative, and I put a 1 here to be consistent, but it's also nice to recognize that you can have more than one alternative. In other words, the drug might actually influence different people in a different way, and so we need to be able to run those kinds of analyses. But at this point, we're just going to have two hypotheses, so that the treatment had no effect, or that the treatment had an effect in a specified direction. This is what I mean. It's pre-planned. So the most generic form of alternative hypothesis is that the mean value is not actually equal to the initial assumed value. So maybe I should highlight that. This is the assumed value for our mean. Okay, this is called a two-tailed test, and I'll emphasize that again in just a moment. This two-tailed test is the basic test. It allows for how should I say? It's the most conservative test. So it's a conservative test, meaning that the likelihood of rejecting something falsely is much lower. But what happens is that we fail to reject the null hypothesis more frequently with a two-tailed test, and that's referencing the power. If we do a one-tail or a directional test, we can increase the power of our test and probably, I should say hopefully, get better results. Okay, so the alternative hypothesis usually is a two-tailed test unless you have definite evidence to suggest you should do a directional or one-tailed test. So sometimes we do, if our initial hypothesis is that the mean value is equal to some specified assumption value. Okay, this has to be known or given. Okay, and we might actually say that we think the mean should be greater than, or maybe we think the mean should be less than the hypothesized value. So these two are one tail, or sometimes we call them directional tests. Okay, and they allow us to do a stronger comparison. Okay, and I want to highlight the example number 15 coming off of page 243, and I want to look at that in a moment. But the idea here is to say that we have choices, and we need to make the choice before we collect the data. Otherwise, I'm going to use the word cheating. It's like having a data set and then analyzing in a way that gives you the result that you think you can get from it, instead of saying, I need to establish this result, now let's go collect data and see if we can. I don't know if that's a distinction that everybody follows, but it's like knowing the end result and saying, yeah, that's what I meant, instead of saying, this is what I'm going to say and this is what I want to show, and then actually establishing it. There's a lot more validity if you have research suggesting one idea, and then you find data that then kind of as a second source supports your idea. All right, so this is the alternative hypothesis, is the pre-planned hypothesis. It is imperative that we remember that a one-tail test gives us different results than a two-tail test. Okay, and that's coming down to the computation. Now I want to make a comment about error. So there's a potential for always making a mistake in statistics and hypothesis tests directly, and so the idea is that we have two types of error, and I just want to focus on type 1 error. Type 1 error. This is the error that we want to minimize the most, and it goes with the idea of falsely rejecting the null hypothesis when it's true. So we want to minimize this false rejection when it's really true. And the way we do that is we set a significance level. Well, we don't always have to, but the significance level alpha is precisely the amount of type 1 error we're willing to have. Type 1 error that is acceptable. It's the end of the day. All right. So the idea with this is saying, okay, if our significance level is 5%, that means we're allowing ourselves the 5% chance of falsely rejecting the null hypothesis. Okay, so when we established a p-value, let's say our p-value is 2%, what we're saying is that our p-value 2%, the likelihood of observing the value that we did see occurs 2% of the time or less, and that is a less risky thing than the set significance level of 5%. So what we're saying is that based on our data, we're actually making type 1 error less than 5% of the time. Therefore, we can say with more assurance that the null hypothesis is not true. Okay, in other words, we reject the null hypothesis. We don't know for a fact exactly what mu should be, but we just know that it's not whatever it was given as. Okay, so just to clarify a bit, with the significance level, we have z-scores that correspond to significance level, and so for the two-tail, if we had an alpha of 5%, we would have a z of plus or minus 1.96, so that's the two-tail. So in other words, the picture is, here's our center at 0, here's negative 1.96, here's positive 1.96, and between those two tails, we have 5% of the observation. So in other words, in here we have 2.5%, and in here we have 2.5% of the area. Okay, so between the two tails we add up to 5%. Now if we had an alpha of 0.01, our z-scores would be plus or minus 2.58. If we had an alpha that was really small, 0.001, our z-scores would be equal to plus or minus 3.30. By the way, I'm pulling this from figure 8.5. I had to remember. And I didn't write down the page number, sorry. Okay, figure 8.5 has all this information listed out. So we're saying that these z-scores would create the boundary line such that the two tails would collectively add up to the right significance level. Now if we had a single tail, let's say, so for one tail, the picture is going to be that single tail, and so if we had an alpha level of 0.05, our picture, we're saying what's the z-score that correspond, and I'm just going to do the upper tail, by the way, you could do it the lower tail. So this here, we're saying all of the probability is secured in that tail, so 5%, so the z-score that corresponds with that would be, well, depending on if it's a upper or lower tail, it's 1.645. By the way, I pulled these from the table in the book, in the back of the book. This is table Appendix B. Statistical tables. This is table B1. Okay. Now, if we had an alpha of 0.01, the z-scores corresponding to that would be plus or minus 2.33. So again, if you had, this would be 2.3, sorry, this would be 1.645 if you had a new picture. So depending on the tail that you want, 0, here's my upper bound, this is 2.33, negative 2.33. So a one-tail test, if for example my null hypothesis was that I think the mean should be, that the mean is less than or equal to some hypothesized value, and my alternative is that the mean is actually greater than the hypothesized value, then I'm looking at this one-tail test up here, and I think it's nice to note that the corner of the inequality points at the tail. Okay, and what we're saying is that in here we have 5%. Okay, now if we had a different null hypothesis and that hypothesis was that the mean should be less than some value, then we're looking at the one tail that's below, and again in here we should see 5%. Okay, the idea that we have is to say, depending on the test, our p-value is either going to be the localized tail or maybe it's the sum of the two tails. So let's look at an example. I think the p-value is very straightforward to compute, so I'm going to do the two-tail test for number 15, and then I want to show the one-tail test. Okay, so let's see here. Let me get a good color. Look on page 243, and this is number 15. All right. So the idea here, you can read through this problem. Researchers have noted that as people age, their cognitive functioning ability decreases. So if we can introduce some ingredient into their food, or just give them a medicine, we can potentially stop that decline in their cognitive functioning. So what they did is they took a sample of, I'm going to switch colors, they took a sample of 16 elderly people and administered some what is it, antioxidant concoction, and they found that when they gave them this test of cognitive ability, the average score was a 50.2. Okay, so this was after the treatment was given. Okay, so a sample of 16, they gave them this test, and after the treatment, the test average was 50.2. Now, they knew from previous information that in the population, the average score on this same exact test, the average score was 45 with a standard deviation of 9. Okay, so they knew this information. This was known. Okay, so what they said is, okay, well, if in our sample of size 16 we observed a mean of 50.2, how likely is that? Okay, so in other words, they want to come up with the p-value, which tells you the likelihood of observing a mean score greater than or equal to 50.2 in a sample of 16 from the population that's distributed normally with mean of 45 and standard deviation 9. Okay, blah blah blah. We want to find the probability, like how likely is it that we would see this be our score. And so let's just compute, and they give us a significance level, and I'm going to ignore that for a second. Let's look at the two-tail test. The reason why I'm looking at the two-tail test is I want to go in without some leaning that says that the people should do better or worse. Mainly because I want to know for either way. In other words, maybe our intervention made it worse. Maybe the people thought, oh wow, I'm going to take this drug and then take a test, I better do better, and then the stress made them do worse. And so just to kind of block out and not have any sort of lurking variable influencing, we're going to do a two-tail test. So in other words, our assumption is that the mean is equal to 45, and this is the known value. Okay, we're going to run it against the alternative, and this is the two-tailed test. We're going to run it against the alternative that the mean is actually not 45 after the treatment. Okay, in other words, I'm not saying that it's greater than 45. I'm saying that it's just not 45. So it could be greater than, or it could be less than. Okay, and of course our data suggests greater than, and so we might then want to, the temptation is to put the directional tail, and in fact we'd want to use the mu is greater than 45, but that's using the data after the fact. Okay, so before we went into this, if we wanted to, we could say, you know what, we really think based on some other evidence that the antioxidant is going to increase the scores, and so we could go in with that assumption already established and then test it with the data we got after we've already created the assumption. Okay, so the two-tailed test, we would come up with this probability. We would say that the probability of observing the mean, okay, greater than or equal to 50.2. Okay, we want to come up with that, and that's going to be our p-value for the one tail. What about in the other direction? And I'm not gonna list it out just yet. Let me clear this. To find the two-tailed test, we're going to double whatever we get here. So for ours, for the two-tailed test, the p-value is going to be twice the p-value from the one tail. Okay, it's kind of an interesting thing, and it's not helpful to write it out, but I just want you to know. So in other words, extreme in the idea is how far away is the 50.2 from the mean, and then maybe we go below that same amount, and what's the likelihood of being that far in general. So let's compute the z-score, and then it'll be easier for me to convey the two-tailed test. So the z-score would be 50.2 minus the mean of 45 divided by the standard error, right? This is a sample mean drawn from a sample size of 16, and so this is going to be the standard deviation divided by the square root of 16. You do the computation and you come up with a z-score of 2.311. What does that tell you? It tells you that 50.2 is 2.311 standard deviations away from 45 and above that. So in other words, to do the two-tailed p-value, we'd want to look above and below that distance. So what's the probability that we have a z that is less than or equal to negative 2.311 plus the probability that a z is greater than or equal to positive 2.311, and that would be the p-value for the two-tail test. Okay, so it's nice that these are actually the same, and so that's what I'm referencing up here. We just doubled the p-value that we get. So what is the p-value? What's the probability of observing a 50.2 when the mean is 45? So the probability of z being greater than or equal to 2.311, if you look this up in table B1, you find that that probability is 0.0104. Okay, notice this would be it. That would be the p-value for the one tail. Let's look at it for the two tail. And so the p-value we actually want, so the p-value for two tail test would be twice that. So p is equal to 0.0208. So in other words, just barely over 2.8% of the time, just barely over 2% of the time, we would observe a value as extreme as 50.2. That is very unlikely. You know, 2% of the time, that's a very low percent of the time. But you know what? In application, you would need to establish what unlikely means for your field. So in other words, sometimes in business, 5% is fine. Sometimes in business, 10% is fine. In other words, if our p-value was less than 10%, we're totally okay with that. But in manufacturing, so think really detailed manufacturing, a 2% error is really a lot. I mean, you would have to be very precise, and so the margin of error that we'd be willing to accept would be much, much lower, and so our significance level might be a 0.0001. Okay, that was kind of a lot, 0.0001. So 1/10,000ths. So in other words, if it's like a clean room or something, that's saying that you would allow one particle of dust for every 10,000 particles of air, something like that. Okay, so that's a very low value, and so depending on the context in nursing, you might just stick with the standard 5%, but I think it's better to just report the p-value and let somebody interpret your results. Okay, so our interpretation then, just based on the p-value, we would say, switch the page here, having a p-value of 0.0208 is enough evidence to reject the assumption that HO is true. So in other words, we are accepting, well, I'm not even going to say that. We're rejecting HO in favor of the alternative. In other words, that the mean is not 45. What we would need to do now, okay, so next step in research would be to repeat this. Repeat the test. I don't mean test, I should say repeat the experiment. I don't know if I'm spelling that right, it doesn't seem right. Experiment, whatever, and you can figure it out. Repeat the experiment and use the specified alternative that the mean should be greater than 45. Okay, so real quick, there's another idea coming out of chapter 8. That's the idea of Cohen's D, to measure effect size. So Cohen's D, which measures effect size, in absolute magnitude. In other words, we're not going to scale it by the standard error. We're going to scale the difference between the means just using the standard deviation. Okay, so this is disregarding sample size. Okay, it's a very straightforward computation. D is equal to the difference in the means divided by the standard deviation. Okay, so for our example, number 15 that we're just finishing, the D value, the effect size, would be the difference in the means, 50.2 minus 45, divided by the sample, the standard deviation of 9. Okay, I didn't do the computation ahead of time. I should have. Sorry, 50.2 minus 45. So the effect is 0.57 with a bunch of sevens. Let's just round it to 578. Okay, grand. What I want to do now is look at chapter 9.